So we have seen how the fraction behave n epsilon over n and n0 over n behaves. We now want to look at the energy, and the energy is, as usual, the energy is sum over epsilon n average of n, which is occupation number, and this becomes a continuous, using the continuous density of state. This goes to g epsilon d epsilon times epsilon divided by z inverse e to the power beta epsilon minus 1. So that we write down this as g epsilon is half 1 over h bar omega naught whole cube integral 0 to infinity d epsilon epsilon square times epsilon divided by z inverse e to the power beta epsilon minus 1. Now, as usual, we will say we'll use the transformation of variable x equal to beta epsilon, so that I have 0 to infinity 1 over beta d of beta epsilon, and then I have an epsilon cube over here, so that makes it beta epsilon whole cube, and I have 1 over beta cube z inverse e to the power beta epsilon minus 1. Sorry, there is a cube outside and over h bar omega naught. So this becomes half the beta cube, and beta gives you beta to the power 4. So I have h bar omega naught whole cube 1 over beta to the power 4 0 to infinity dx x cube z inverse e to the power x minus 1, which we rewrite as kbt over h bar omega naught whole cube times another factor of kbt, and then I am left out with half 0 to infinity dx x cube z inverse e to the power x minus 1. Clearly, this integral is related to my function fm plus of z, which was 1 over m minus 1 factorial 0 to infinity dx x to the power m minus 1 z inverse e to the power x minus 1. Now you see that whatever I have within the integrand tells me that this is f4 plus of z, but the factorial does not match. This is 3 factorial. For f4 I have a half. That is easily remedied by bringing a 3 factor in the denominator as well as in the numerator. So I have 3 kbt over h bar omega naught whole cube, and I have f4 plus of z, and this is my energy I'm looking at. Now the idea is, for t less than tc, I know z goes to 1. Therefore, my f4 plus of z, since m is greater than 1, as z tends to 1, this function value goes to zeta of 4. So I will replace this by zeta of 4, where I write down this as 3 kbt zeta 4, and then I have kbt over h bar omega naught whole cube, so that u is equal to, let's say, 3 zeta 4 kbt and kbt over h bar omega naught whole cube, which implies the the internal energy scales with T to the power 4. The specific heat at constant volume is given by 3 zeta 4 is del U del T, so that I have Kb, let's keep Kb over here, and then I have Kb over h bar omega naught whole cube ddt of T to the power 4, and that is 12 zeta 4 Kb Kb T over h bar omega naught whole cube. So this derivative brings in a factor 4 times T cube, and this T cube I reabsorb in the bracket to recast my equation for specific heat in this way. Now, if you recall, your N particle number was kBT over h bar omega naught whole cube F3 plus Z. For T greater than Tc, from this is the equation from which you have to determine the fugacity. But for T less than Tc, my life is a little bit simpler, because this function now becomes zeta of 3. So that N is equal to kBT over h bar at Tc. We will substitute for at Tc whole cube zeta of 3. Therefore, I can immediately see the expression, and I can see that Kb over h bar omega naught whole cube is nothing but N over zeta 3 and 1 over Tc cube. So my specific heat becomes 12 Kb zeta 4, and then I have N over zeta 3 1 over Tc whole cube times T cube, which takes a very simple form, which gives me 12 N Kb zeta 4 over zeta 3 times T over Tc whole cube. So that C over NKB is going to be 12 zeta 4 over zeta 3 times T over Tc whole cube, and exactly at T is equal to Tc, the specific heat is given by 12 zeta 4 over zeta 3. The specific heat for T less than Tc would scale as T cube for T less than Tc. What about the high temperature case? Well, for that we know that U was given by 3 kBT over h bar omega naught whole cube F plus 4 of Z, and N, this is the case where we are looking at T greater than Tc, and N is given by kBT over h bar omega naught whole cube F3 plus Z. So I can now eliminate this kBT h bar omega naught, which is over here. So I can write down kBT over h bar omega naught whole cube as N over F plus 3 of Z. And I have the expression U is equal to 3 kBT times N over F plus 3 of Z times F4 plus of Z. Therefore, U over NKB is going to be 3T times F4 plus of Z and F3 plus of Z. So we want to do repeat the elaborate calculation, and it's instructive to do it The specific heat C over NKB is going to be del T of U over NKB. This means this is going to be del T of 3 times T times F4 plus of Z, F3 plus of Z, which simplifies to 3 times F4 plus of Z divided by F3 plus of Z. First the derivative with respect to temperature, and then you have plus 3T divided by F3 plus of Z whole square times F3 plus of Z dF4 plus dt minus F4 plus of Z dF3 plus dt. Let's be careful with this to see whether everything is consistent now. So that C over NKB is going to be 3 F4 plus of Z F3 plus of Z plus 3 times T F3 plus of Z dF4 plus of dt minus F4 plus of Z dF3 plus of Z dt divided by F3 plus of Z square. Now I know that ddt of Fm plus is 1 by Z Fm minus 1 plus of Z. This we did in the previous lectures, times so now I know that ddt of Fm plus is ddz of Fm plus and then dz of dt, and dFm plus dz is going to be 1 by Z Fm minus 1 plus as Z, so that this becomes 1 by Z dz dt times F plus m minus 1 of Z, and this implies that F plus 5 F plus, so I have a derivative of ddt of F plus 4 of Z, which is 1 over Z dz dt times F3 plus of Z, and ddt of F3 plus of Z is going to be 1 over Z dz dt of F2 plus of Z. So we are left to determine these derivatives. Now in the ideal Bose gas, we have seen that this derivative dz dt is minus 3 over 2t F plus 3 by 2 divided by F plus half. So word of caution is do not use this here because you have different density of states. Please be careful in blindly using results. Instead, we start from the same starting point from where using which we derived such a relation, that is to look at the particle number. Particle number is given by, for a harmonically trapped Bose gas, is given by kBt over divided by h bar omega naught whole cube times F plus 3 of Z, so that I have n times h bar omega naught kBt whole cube is going to be F of F3 of Z. Now let's take a derivative with respect to temperature, both in the left hand side as well as in the right hand side. And let's look at the left hand side. The left hand side is ddt of n h bar omega naught over kbt whole cube, which is going to be n h bar omega naught whole cube d dt of 1 over t cube, and that's a straightforward derivative. You're going to have minus 3n h bar omega naught whole cube divided by t to the power 4, and I have missed a kb over here, so that this kb 1 over t to the power 4, so that I have minus 3 over t times n h bar omega naught divided by kbt whole cube. But if you look at this expression, then kbt h bar omega naught whole cube is going to be n divided by f plus 3 of z, and therefore you have the answer minus 3 over t times n, and I'm going to use this expression over here, noting that what I have here is just 1 over this value, the left hand side, so that this gives me f plus 3 over z divided by n, and this answer is minus 3 over t f3 of z. The right hand side is d dt of f3 of z, and that is going to be dz ddz of f3 of z times dz dt, and this derivative is 1 over z f2 plus z times dz dt, so that the left hand side is 1 over z dz of dt times f2 plus z. I can take this, combine this to give me 1 over z dz dt is equal to minus 3 over t f3 plus of z divided by f2 plus of z. So once I have this, I take the expression of the specific heat, which is going to be 3 f4 plus divided by f3 plus both functions of z plus 3t. Let's just write it down once again. It's a little bit laborious, but it's okay. So I have f3 plus of z df4 plus dt minus f4 plus of z df3 plus dt divided by f3 plus of z whole square. Let's take this expression and carry forward the calculation. I know that I have the left hand, I have this part, we will add it at the right time. So this is 3t times f3 plus of z, and this is ddz of f4 plus times dz dt minus f4 plus of z dz of f3 plus times dz dt divided by f3 plus of z whole square. So that this is 3. This I already know, this derivatives. This derivative is 1 by z f3 plus of z, and this derivative is 1 by z f2 plus z. Therefore, I have 1 over z dz dt that comes outside as a common factor, and then I have f3 multiplying f3 giving me f3 plus z whole square minus f4 plus of z f2 plus of z divided by f3 plus of z whole square. This also I know. I just calculated 1 by z dz dt, and the answer is this. So I take this and substitute over here to give me 3 times t minus 3 by t f3 plus of z divided by, I have f2 plus of z. And this is 1 minus f4 plus of z f2 plus of z divided by f3 plus of z whole square. So that this expression tt gets cancelled out, and the first term you see is minus 9 f3 plus of z divided by f2 plus of z. The second expression is plus 9 f4 plus of z, and if you see that this factor of f3 plus now cancels one factor of f3 plus from the denominator, and the f2 plus completely cancels the f2 plus over here, so that you have f3 plus of z. Now look at it carefully and see. Let's add the first term. The first term is 3 f4 plus of z divided by f3 plus of z, so that this and this are the same terms, well, same forms. Therefore the specific heat now becomes 9 plus 3 is 12 f4 plus of z divided by f3 plus of z minus 9 f3 plus of z divided by f2 plus of z. Question is, this looks very nice. Now we got to check whether we have arrived at the right expression. So for that, the first thing to look is the high temperature expansion. Sorry, the high temperature limit. And in the high temperature limit, z is very small, and I know that all of this Fm plus z is approximately z, so that the specific heat C over NKB reaches 12 minus 9, which is equal to 3, and this is the classical result, which is C is going to be 3 NKB. Now is the interesting thing is what happens at T equal to Tc. At T equal to Tc, one has C over NKB as 12 times zeta 4 divided by zeta 3 minus 9 times zeta 3 divided by zeta 2, the Riemann zeta function. And here it is interesting, because I clearly see that there is a difference, right? There is a difference, and this does not match the specific heat which we obtained at T equal to Tc, which was C over NKB was 12 by 4 zeta 4 over zeta 3. This is the result of the specific heat at Tc approaching from Tc minus. So you are approaching the critical temperature from below the critical temperature, and once you do that, this is the result that you get. In contrast, specific heat at T is equal to Tc when approaching from TC plus. So this is your TC. TC plus is approaching from this, TC minus is this, and when you approach from TC plus, you get this expression. So there is a difference, and that difference, delta C over NKB, is 12 zeta 4 divided by zeta 3 minus 9 of zeta 3 divided by zeta 2 minus 12, sorry, this is just 12, not my mistake, minus 12 zeta 4 over zeta 3, which is minus 9 zeta 3 over zeta 2. So there is a discontinuity in the specific heat. In specific heat at the critical temperature T equal to Tc.